But yeah, so I'm Aaron Su, and I'm presenting some work that Rodrigo and I did, working on exploring some deep learning applications with APL. So the basic summary of this is we asked, what would it look like if we decided we were going to just, from scratch, try to do a non-trivial neural network application in a deep learning space with pure APL, no anything else, just write it as if we were starting from scratch, and what would that look like? So that story sort of has a few components. Is this kind of small for you guys? I feel like the resolution could be a little bigger. Anyway, it shouldn't be too bad as we get into it. But basically, we wanted to ask, what is it that we know already about the state of learning frameworks? And then what do we want to try to find out from this APL stuff? And how do we explore that? And if we have any conclusions on that. So what do we know right now as far as our impressions going into this of the state of deep learning? And we can really summarize that as like just deep learning means you've got a bunch of people competing in this space with various types of frameworks. And that has the same implication across the board, right? So the fact that these learning frameworks dominate, we can say comes from a few reasons, but also has a few important carryovers. And so one is the frameworks are written usually because we have this impression that writing something from scratch in the deep learning space is difficult, right? And two, when we do implement it from scratch, usually the performance isn't very good, right? So I can, most of the time if you look up online and look for somebody who implemented a network from scratch, they were like, oh, it's cool, it works, I figured it out, and it runs, you know, like a turtle. It runs like a turtle in molasses trying to go through spaghetti in a tornado, right? It's just terrible. So, but the reason you might want to do that, not just, you know, at a professional level, but especially from an educational level, is we're at a state in learning education with deep learning that people are becoming specialists in frameworks and learning how to apply the frameworks, but they don't necessarily know why anything works, how it works, or are able to really predict the behavior of any of these systems, in large part because they are button mashing, right? And what we get from this lack of insight that you gain from these very black box frameworks is that we do have a lot of button mashing. We have a lot of people that can get by just playing around. And so again, thank you to Rodrigo for this little find. But there's a very real sense in which people just sort of mash their networks together and hope for the results they want, and then they play with some parameters, and they get trained on guessing the right parameters more frequently than they guess the wrong parameters. And that's kind of, you know, if everybody's doing that, you know, my philosophy is that, you know, if we're all doing exactly the same thing in the exact same way, maybe there's an opportunity to try something else. And that's really where we're starting with this. And we're particularly looking at it from the angle of how your vertical agility is limited by sticking to a framework-based model. So especially a black box framework. So if you're limited in a black box framework, you're going to be limited in the amount of insights, particularly vertically in terms of applying domain insights up and down your stack. So we wanted to see what the potential was if we could find a way to reduce the need for a black box framework. So how are we going to try this? What's different? Well, you know, obviously, if anybody knows me, we're going to try it in APL, and we're going to see what happens. And traditionally, there's some precedence for this because APL was part of the original neural network boom, if you can call it that, in the 80s. But, you know, it had the same problems that all of the systems had at that time, which was that you just couldn't get the performance that you needed, right? And this was especially true since APL has been an interpreted language, especially in the 80s. There wasn't anything available to help speed that performance up. And we wanted to look at this from a scratch system and completely ignore the typical approach of building up frameworks and libraries and techniques and anything that was specialized to the deep learning space. And we wanted to say, well, how hard is it if we don't do any of that stuff? And we were going to build this on the idea that we now have APL compilers. And given that we now have some APL compilers that target the GPU, what's the state of the APL community or the APL ecosystem when applying to this kind of stuff? So what did we do? Well, we specifically looked at the UNet CNN, which is a pretty well-known image segmentation problem with a non-trivial but still accessible level of complexity in its network. And we philosophically said, we are not going to try to be clever here at all. We're going to be naive in how we implement this stuff in the APL. So we went for the simplest possible solution, and then we used the Co-dfns compiler to produce it, and then we compared that against a PyTorch implementation. And we were interested not just in the performance of these two systems, but what it felt like to actually use them. What would it be like if we tried to do this? Is the from-scratch implementation in APL even remotely close to usable compared to some of these frameworks? So performance-wise, we actually didn't do too badly. So that top big giant bar there at the end, that's the runtime performance of the Dyalog APL interpreter. So that's sort of our traditional APL implementation targeting the CPU with very little GPU deep learning type of optimization, basically none. And it gets very poor performance on a single forward and backward pass over this UNet computation. So like what you would do with a very single training loop before you update your weights. You would run one of these forward and backward propagation passes. So the Co-dfns compiler on just the regular CPU, which was single thread, about doubled that performance. And if we run single thread with PyTorch, it about doubles that performance over the Co-dfns compiler. And then when we get down to the GPU side, we see that the Co-dfns compiler on the GPU is within a factor of about 2.2, 2.6 of the PyTorch implementation. And given that this was a from-scratch implementation that was completely naive, so we didn't do any optimizations really of the code, we just tried to express the code in really simple ways with minimal tricks. So we tried to keep the code nice and tight and clean. This was pretty good. In particular, the Co-dfns compiler itself has no special optimizations at its layer. Right? It's a relatively naive compiler intended to be fairly straightforward and predictable. So we get pretty close even despite all of that. And so for those who aren't familiar with the UNet, this is the kind of system that we were working on building. And each of these is one of our layers, and then we had a set of 5 different computations that we had to do. 3 different types of convolutions, a max pool layer, and a copy and crop, for those who are familiar with those operations. And we had to think about how do we design the wiring to this, but also how do we implement each of those particular operations. And we go into detail in the paper how this code works, but just to compare the code sort of a little bit, here the APL code came out to about 23 lines of code. The PyTorch implementation came out to about 95 lines of code, give or take. And this is sort of the difference of how they look. So this is the 2D convolution over arbitrary channels, and this sort of, we can compare a little bit how they look. And so one of the things, for instance, that we did is we didn't rely on any sort of auto differentiation. So we have to implement both. Oh, I can't walk, can I? All right. They've got me stuck to the mic here. Okay. So you implement both the forward and the backward passes. The what? Yeah. Can you see that? No, you can't see that. Wait, but there's a pen. There's a laser pointer. All right, there we go. So the CV is the forward propagation pass of a 2D convolution. So that's equivalent to your conv 2D kind of thing. And you can see this is the full implementation in APL. It's very, very simple, and that exposes a lot of understanding of how the whole system works. But we don't have any auto differentiation, so you also have to implement the back propagation pass as well. And then if we compare that to sort of what it looks like to make a function call to the API in PyTorch, this is sort of what it looks like. You have to chain, in this case, the CV has a ReLU in it. And so you have to include the ReLU for the network and the convolution. And then you have to sort of parameterize it over the number of input and output channels. This here, implied in this code is that it's a 2D convolution, and that it's a deep network, that your base channels, you've got an extra channel for your layers, but absent that, it's abstract to any other size of your layers. So the dimensionality of this can scale up to as many different dimensionalities as you want, versus something like PyTorch, which is much more constrained, and you have to specify the in and out channels explicitly through these in and out channel parameters, whereas this is agnostic to the number of channels in its implementation. So the complexity here, just calling the API is simpler from a pure, complexity standpoint. The tree is simpler and things like that. But the overall visual complexity and other things like that, the APL for being a complete implementation of the concept is not as complex as you might imagine, which makes this pretty accessible. So what do we think about this? Well, from this complexity standpoint, the PyTorch is still probably arguably a little bit simpler, just from a foundational standpoint. But when you realize that the PyTorch is just making a bunch of API calls and the APL is actually implementing the full thing, the complexity there starts to be a really big difference there in terms of usability. And the benefit there, I think we're looking at is especially in the type of insights that you can gain into your code from an educational standpoint, from teaching people neural networks, but also as a domain expert, if you want to have more control over composing your system together and making more insights, you can layer algorithms and insights from your domain into your system without having to have this hard barrier between what's happening in your net and what's happening outside of your net, which currently the frameworks force you to have that. And here you can fuse and merge and apply a whole wide range of techniques and strategies and insights into your networks that you might not otherwise be able to do. And that gives you, at least ideally, in theory, that can increase the amount of exploratory capacity that you have for doing this kind of development. And right now, the performance of these frameworks is faster than what Co-dfns provides, but it's not that much faster. So I think the argument that we would be making is that these, it is pretty conceivable now that we could produce something that is competitive with the framework performance based on an approach like this. We haven't done it yet, but I think at least as close as the performance comes, that's within reach now. But there are some big major questions that we have to sort of answer, and one of them is auto-differentiation, right? Because everybody just assumes auto-diff is going to be around. And it seems like we would want to have auto-diff. How feasible is that for a more general system like APL? If it is feasible, do we really want it, or is there a benefit to not having it? I think there's a bunch of questions we want to explore around auto-differentiation. Also, performance tuning, one of the things that we run into with something like APL is that the design around the integers and the floating point data and how the numeric tower works in APL can present some challenges to getting the high performance while retaining the usability that you get inside of the APL language. And so we have to explore what the correct design for that is to allow you to leverage, say, half floats or these 8-bit floats or the 16-bit floats that people are working with versus, just doubles or things that the neural networks don't care about whatsoever. But we also care a lot about predictability and making sure that the performance you get is something that you can predict ahead of time, and it's not some magic compiler that's producing things that you have no idea why it's doing what it's doing. Now, integration and tooling is also going to be a big thing, but I think we are making a lot of progress in that respect. But clearly, there's a big question of how do you best integrate, say, an APL pipeline into your Python code or other data science stacks or into a larger distributed system. How are you going to integrate all of that? And a lot of those questions have yet to be fully answered, I think. So in conclusion, we think that the APL language and ecosystem is a really fascinating candidate for exploring an alternative approach to solving, sort of these data science-y, data analytics, neural network programming problems by taking a different tack of how we can make these accessible and usable to a wider range of people and maybe adjust where we have to cut our boundaries in terms of teaching and in using and what we can expect professional users to do and what are the jobs and responsibilities of the compiler writer and so on. So thank you, and I'll take any questions. And of course, it wouldn't be a proper APL talk if we didn't throw a slide full of APL up there. So that's the implementation. So, yes.
So thank you for your talk. So I have a question related to the, so you're targeting GPUs here, you said, right?
Yes.
How different would it be if you would target a CPU for the same program? So would you have to change your APL implementation?
No, the APL is agnostic to CPU or GPU execution.
Okay.
Yeah. That's one of the nice things about
All
APL.
right. So there is really like just mathematically specified, and there's.
Just math, yeah.
Okay, cool.
So if you want to see an example of us exploring that space a little bit, my thesis did benchmarking across the two platforms for tree processing.
So for optimization purposes, you rely on the compiler.
Yes. So actually, because of the design of APL, APL is able to do very little compiler analysis to dispatch to very highly tuned and optimized jets or what you would think of as library calls. So one of the advantages of the APL language is it's much easier to take advantage of specialized libraries in the compilation phase with much less compiler analysis overhead required to get there, if that makes sense.
Yeah.
So we can leverage compiler analyses, but we can also leverage pretty much all of the specially hand-tuned libraries under the hood as well.
But so who's making this decision? Is the compiler?
The compiler makes the decision on which specialized libraries to use or things like that.
So it's driven by some models of.
So it depends. So the version that we tested here, which is the version 4 of the Co-dfns compiler, that dispatches based on you tell it when you compile it, you tell it whether we're compiling for the GPU or the CPU, and it builds links against a DLL with the runtime targeting those particular implementations, and then they have specialized runtime implementations for that architecture for the specific libraries that we're looking for. So it's a fairly bulk optimization. The newer versions of the compiler are now doing runtime dispatch to different models and architectures depending on the type of data that it sees coming in at runtime.
Okay, thank you.
I don't know whether Troels would ask this question, but I can see this. I guess it's a forward and backwards and functions for so the automatic differentiated thing here would benefit a lot, right? So I know that Kenneth Iversen had this NAPLA operator, and I think you also have a NAPLA in there, but that's not his.
A NAPLA? Oh, the delta?
No, I think it was a NAPLA. Kenneth Iversen had this computing the Jacobian. Of
this guy or
the operator? It's very low. It's in the second last.
Oh, this guy here.
Yeah, also there. Yeah.
Yeah. So that is co-opted right now as a symbol in formal APL for recursion. So that is a recursive call to the newest function. Yeah.
But Kenneth Iversen also had this differentiating.
Yeah.
So that help you?
So I think there is there's precedence for doing automatic function inversion in APL, and so I think there's an argument to be made that a large swath of APL could be admissible to auto-diffing as well, using an operator in a similar technique to what we do with inversion right now. And I think if we can get that to be wide enough, there's really interesting applications of that because you'd be auto-diffing at the APL layer instead of auto-diffing at the vocabulary layer of the deep learning networks, which might expose more opportunities for differentiation across a wider domain of problems than what the frameworks can provide. But that's an open research future work kind of question. I don't know the answer to that yet.
Is that your question? No.
So the thesis of this work is investigating no framework deep learning, or whatever you want to call it. Right?
Yeah, the thesis is basically what is our baseline that we're at right now,
right?
And what are the paths to maybe going beyond that?
So my question is really, how much of this requires APL, and how much is a question of how you use the tools you might otherwise have available? For example, in your PyTorch example, you used keyword arguments and long names, and you used the built-in convolution definition. Yeah. Could you just use lower-level things in PyTorch or in NumPy, and get the same result? I mean, it would be more of a both, but would it still be a representation of what you're looking for?
Yeah. So this is the perennial, constant question, I think, in terms of these, whenever this kind of stuff comes up, there's always a question of, do we have to do it with these funny symbols and these squiggles, or can we just make library calls out to the correct functions in our other programming languages? And I think a lot of people are exploring that. So I'd say like maybe systems like Julia or the Array'Fire library system, or a lot of other spaces are exploring what it would look like to have a library-based or approach or a DSL-based approach for doing these kinds of array programming questions. But the answer is essentially, obviously, we could always write something semantically equivalent in any language that we want, right? That's a baseline. Anybody could do that. But historically, we can recognize that people don't do that. And there's a question of why they don't do that. And I think that's the real place that APL can explore in more detail, is that there's a reason people don't prefer to tend towards that style of programming in other programming languages. And I would argue that it's a human factors ergonomics question, and that if we improve the notation and the education around how to solve a wider variety of problems using these same techniques, and we get the vocabulary correct and things like that, that these things become more accessible. And I think that's where APL wins compared to other languages, is that you can just use these techniques in more places more easily when you're using the APL notation versus other languages. And that's where the win comes in, because otherwise you're really limited when the verbosity goes up. The usability starts to go way down, and that tends to affect people's ability to work with code that's written that way. That would be my claim, at least. So I don't know, does that answer the question? So.
I think I can ask another. Do you want to ask? Okay, so you kind of, one thing I was wondering, and you sort of answered it a little bit at the end, is AD one of these black boxes that you don't want to support?
AD?
Yeah, automatic differentiation.
Oh.
I mean, it is a big, complicated block, and it's a kind of black box.
Yeah, so it's interesting, is auto-diffing in frameworks is very black boxy, because you're working with very complex operations. But if we can find a way to make AD a more basic primitive that works over more basic elements, and you can reason about that, at a level of, say, like an undergraduate differential equations type of class, maybe the argument might be maybe that's simple enough that people can then use it accessibly. But again, I would argue if we lose that ability and people don't know how it works or can't predict it or can't reason about compositions with the AD operator, say, then maybe it's not a good idea. At least from the philosophy of trying to give people greater insight into their codes. Maybe that's a bad idea. So that's where the question about where autodiff plays a role is big in that. And maybe it needs to be like a transparent library that people can read the source code for and understand. So maybe an autodiffer that is an extra library or a pass that you can go into and actually have a chance of understanding in a week or something like that is good enough, versus some of these systems are architected in such a way that, like, reading the autodiff code is probably impractical for most people. Does that?
Thanks.
Okay. I mean, yeah. Yes.
Are we implementing a large language model next?
Are you up for it? You ready? No, these large language models are interesting, but there is so much work from an engineering side on implementing just the basic APL compilation stuff that, this was doable. Adding a large language model into it, I have to pick and choose my battles. So, yes. All right, thank you. I guess it's lunchtime now, so let's do it.